Welcome to the Sentinel Hub webinar. Today's webinar is a continuation of our previous one, where we introduced you to the QueryPlanet project, a project founded and supported by ESA's PhiLab that aims at facilitating the creation of machine learning application to tackle Earth observation challenges at large scale. And while the previous webinar provided a high-level overview of the applications developed, today we will have a closer look at how such applications are built, allowing you to reproduce the results and build your own application. We will have Ivan from How company. He will show you the nuts and bolts of their super resolution algorithm for Sentinel-2 time series. Benjamin from Vision Impulse will demonstrate how to build a pan-European forest and tree species maps using Sentinel-2 imagery. And finally, Devis from Sinergise will present how to implement an efficient object detection using multi-scale satellite imagery. So without further ado, let's start with Ivan's presentation.
Hey everyone, my name is Ivan, and I'll be walking you through the super resolution example today, the project I've been working on together with Julian Cornebis and Freddy Kalaitz. Briefly about me, I'm a software engineer and an aspiring ML engineer that's just starting out his career. I've done some work and research in a variety of fields, from information security, robotics, autonomous vehicles, and I've even dabbled in fields like computational neuroscience. You can find me on Twitter at the handle shown below, and you can see some of my work at my GitHub profile or any of the links provided. Now, before diving in the example itself, I just briefly wanted to explain what super resolution is, in case someone hasn't heard of it or needs a refresher. So, super resolution is a technique or a class of techniques that enhances the resolution of a low resolution image to high resolution. So it's a way of bumping the resolution of a low-res image to high-res. There are different approaches and techniques, and our machine learning-powered approach is to combine multiple low-resolution images that are days or weeks apart in time to allow the network to infer the information it needs to successfully enhance the low-res images into a single super-resolved image. Now, that might sound a bit complicated, and it probably is. But luckily for us, it is a visual task, and I'm also a visual learner. So let's take a look at some visualizations to get an intuition of how it works. First, here we're looking at the input, or the multiple images I said we're combining to get a super resolved single image. This is what the 4 low resolution images or satellite revisits look like. You might hear me calling them revisits instead of images from now on. But that's exactly what they are, because the Sentinel-2 satellite regularly flies over most points on the planet or revisits them and then snaps a picture of them. So that's our input to the model. Our model merges all 4 of these to generate a single super resolved high resolution image. There's also this video that can help us gain some intuition on how it works. First, we pick some point on the planet, and then we take several low-resolution images of it. We don't mind even if some of them are cloudy, because we are using several, and our model knows to ignore the clouds when generating the super-resolved output. Then, in this case 7, we merge those low-res revisits and then feed them into the trained model. Our trained model then outputs the single super resolved high resolution image. Here you can see the slider that is showing the difference between the super resolved output and the low resolution input. So once again, we take 7 revisits, merge them, and then feed them into the model, and then it puts out this merged super resolved high resolution image, which is a single image. All the user needs to do in order to get that super resolved image is just to select a point on the planet, and our example notebook does everything for you. A point on the planet that interests us is appropriately called a point of interest, or a POI. which I might call them from now on. And a POI, or a point of interest, is defined by its coordinates, its longitude and latitude. But you don't even need to know those from memory to use the example. You can just click on a map and it will get them for you. But more on that later. Now, there is a bunch of steps we need to do to get from the lower resolution input to the super resolved output. For those of you familiar with EO-Learn and Sentinel Hub, we're relying on them to find and download all the available Sentinel-2 imagery for us. And we're using EO workflow to nicely connect all of the tasks together into one workflow. But don't worry if you haven't used EO workflow or anything mentioned here. You don't need to know any of the details. The Jupyter notebook for the example does everything for you. This is just if you find yourself wanting to customize or extend anything, and it's pretty simple to do so. We'll also go through the code step by step later on. So just to reiterate, everything shown here is automatically done for the user. The only input the example or the pipeline needs is just a point of interest from you, or a list of points of interest if you'd like to do several. Okay, so the first thing we need to do is generate a box around our POI, or an area, that converts our points of interest into areas of interest. You can use any area you'd like. We usually use 2.5 square kilometers. And that allows us to search the Sentinel-2 catalog for available revisits of our AOIs. Also, Sentinel-2 is an ESA mission that consists of 2 identical satellites in the same orbit, whose purpose is to regularly revisit and image almost all points on the planet. And the best thing about Sentinel-2 is that its images are completely free, which is why we're using it here. And we're also using Sentinel Hub to find and download the revisits for our AOIs. Now, since the 2 satellites I mentioned regularly revisit almost any point on the planet, there's usually a lot of revisits available, and our model needs just a few. So we'd like to filter these to get the most relevant ones for us. We usually try to get revisits that are closest to some target date. That allows us to get a closer representation of the AOI on that specific date. You can use any date you want, but by default we use today's date, which means we would like our super resolved image of the AOI to look as close as possible to what it looks like today. The selected revisits are then automatically downloaded using Sentinel Hub, so they can be used as the inputs to our model. And finally, the downloaded revisits are input into the model, which generates a single super resolved high resolution output. The output is then exported and saved as an EO patch, which is designed to store all types of Earth observation or EO data for a geographical location. And for those of you familiar with EO-Learn, every step shown here is an EO task wrapped by the EO node class, which allows us to use them through an EO workflow. And that's the entire process explained. As I mentioned earlier, this is all done automatically, and the user isn't expected to understand, modify, or adapt any of it if they don't want to. And before jumping into the code itself, I'd just like to mention that we're still fine-tuning our model, and the model I'll be showing you today is an earlier model trained on the SpaceNet 7 dataset. The final model, trained on our new 10,000 square kilometer dataset, along with all of the code and the scientific paper explaining everything, will be released sometime mid-May. Okay, so we can jump into the code then. The example comes in the form of a Jupyter notebook, and everything I've said before is also written down a bit more formally here. The description briefly explains the pipeline and goes through all of the adjustable parameters in case someone wants to use a different type of imagery with it. And like we said, the first thing we need to do is select a location on the planet that we'd like to get a super resolved high resolution image of, point of interest. And we can use this map here to select one. Let's select somewhere in London. Here. The map provides us with two variables that we can just copy and paste into the code below. And that's basically everything the user needs to do. The rest of the pipeline is automatic, so all you need to do is just plug in the coordinates of your POI here, and that's it. You can also see a visualization of your POI here below. Okay, I've run the rest of the notebook now, and we're gonna wait for the result. It takes about 30 seconds to run on my laptop notebook CPU, when it's not a recording a video, that is. We focused on making the model usable by anyone, even without a GPU for inference, so it can be ran in a minute or two. And it can also be fully trained with a single GPU in a few hours. And while we're waiting on the example to run, which again takes about 30 seconds on my laptop CPU when it's not recording, we can take a look at the workflow steps, which are, for those of you familiar with them, EO tasks, whom we will later wrap around using the EO node class. The first task here converts our POIs into AOIs. The second task searches the Sentinel-2 catalog for revisits using Sentinel Hub. The third task selects a few revisits from the large number of revisits that are available. The fourth step downloads the selected revisits. There's also an additional step here that allows you to skip the first 4 if you already have your own imagery in EO patches that you'd like to use. And then the fifth step is finally the super resolution one. It loads up the downloaded revisits, loads up the model, and then generates a super resolved output by inputting the downloaded revisits into the model. And the sixth and final step exports the super resolved high resolution image to an EO patch and then saves it to disk. And here's where we wrap the tasks we defined above, the 6 of them, into EO nodes, and we connect them using an EO workflow. The EO workflow provides a really simple way to connect a series of interdependent tasks, and it also allows to use the outputs from some tasks as the inputs to other tasks. And then finally, we can visualize our inputs and our outputs. Here's what a single low-resolution input looks like. Here's the all 4 of the low-resolution revisits that we used as the input to our model. And finally, here's the super resolved output. Like I mentioned earlier, the project is completely open source, and we're targeting a mid-May release of the Python library that we made and used to generate our dataset and train our model. At the same time, we will also be releasing a dataset of 10,000 square kilometers of high-resolution satellite imagery, a super-resolution model that we trained on it, and a scientific paper that describes all of it. And that would be it for this example. Thanks for your time. In case you've got any questions, you can reach Julian at the Twitter handle and email address provided below. And you can also reach me at the Twitter handle and email address provided below. Thanks for your time.
Thanks to Ivan for his prepared presentation. So let's continue with Benjamin's part.
So my name is Benjamin. I'm from Vision Impulse. I will present today, similar as in the talk before, a Jupyter notebook, IPython notebook, on how you can basically generate with Sentinel-2, EO-Learn library, and typical machine learning frameworks, such a map that we can see over here. So this is what we presented in the last seminar. It's using multi-temporal Sentinel-2 imagery. And today I will show on a very selected area here how you can train and inference with this kind of library over such an area. So let's go directly to the IPython notebook that I have prepared here. For this example here, for the forest type segmentation, we have three bigger parts that I would like to focus on. So the first one is about the data acquisition from Sentinel Hub. So this is where we get the Sentinel-2 multi-temple patches from. And then we have a second and a third part focusing on the EOLearn library, on how you can basically train such multi-temple models. In our case, we also use PyTorch as a machine learning framework. And then also, once you have such a trained model, how you can also inference on new areas, for instance. So here you see the main packages that are required for this notebook. So mainly from the EOLearn library, also Sentinel Hub, and a few geo packages. Before you also start with this notebook, it's also important that you set up an account for Sentinel Hub. So typically, when you register there, you get some OAuth credentials, the ID and the secret. So you have to set these parameters over here and generate this instance. And then we are basically ready to go for the notebook. So the first part about the data acquisition, we prepared here in this AWS bucket also supplemental material. So here you will find the geo package for the area of interest that we are focusing on, and also the model weights of the machine learning model that we also released. So this area of interest that you can see here, Kaiserslautern, that's where we're coming from in Germany, and very nearby is one of the largest forests in Germany. So yeah, that's why we took also this area. So let's get here an overview. Here we can now download the very first geo package, which represents the area of Kaiserslautern. Take some time. Okay, it's downloading, so it's a bit bigger file. And with this geo package here, we can extract the area of interest. So this is basically the boundary of this interest that we have. Here you can see a visualization of this area. So it's a large area. And the next part, it's quite important. So when we have such a large area, typically it's hundreds or thousands of square kilometers. And if you process this kind of imagery, also with respect to if you have additional temporal dimension, you typically have problems feeding this into your network or your RAM. So it's typically important to also split these areas up into smaller patches. And this is what we are doing here in the next step. So here you see a UTM zone splitter. It's taking basically this area of interest that you can see over here, and it creates smaller 5 square kilometer patches out of it. So here we define this splitter. From the splitter, we get the bounding boxes for these smaller patches. And then we basically just write here this grid that is generated by this splitter into a new geo package. It's basically what you can see over here. And next, we also visualize now this grid. And here you can basically see again, these are the 5 square kilometer patches over Kaiserslautern. So you also remember the shape here, which corresponds to this shape here in a large area. And now we can process these individual patches quite easily and feed it into the machine learning models, feed it to the memory of your computer, and so on. So the next step, now that we have set up this grid here over our area of interest, is to start downloading the Sentinel-2 imagery for each of these patches here. So therefore, we defined here from the Sentinel Hub package, a import task, which is basically defining what kind of information we want to retrieve from Sentinel Hub. In our case, we rely here on the 10-meter bands, so BGR and near-infrared band. We just select the images with a certain cloud cover, and that's it. Yeah, that's it mainly. So this is the first task that we define, and the second task is a save task, which basically stores our downloaded images into this folder here, EU patches folder. And similar as in the talk before, once we have set up these tasks here, we can define certain nodes, for instance here a download node or a save node, and then connect them over using a graph structure and define here a workflow. So in this workflow, we first download for one patch the imagery and then just store it. Typically, it's also quite important to scale the data, and this is also something that we can directly do. So here you see, for instance, some additional task, for instance, a scaling task, which is scaling the raw input data that we get. And we can simply, if we see here again at this workflow, so after downloading, we scale the imagery to a certain degree, what we want, and then just save it. And of course, again, we define here 3 different nodes, connect them, and then we can run this workflow. Now, once we have set up now this workflow here that I just mentioned, so in this case, downloading and saving this information, we have the only thing that is left basically is to define which kind of bounding box we want to get. So if I go up to this grid here, so we can run this now over all of these patches that we can see here. For the sake of this notebook, we just cropped out a smaller area. So we're just selecting these 16 patches over here. But in general, it can run also over the complete area. It's just that it's running faster if you want to also try it. So therefore, we define here the tile IDs very specifically, and then just execute this workflow for each of these IDs here. So for each ID, we get the bounding box over here. We download the corresponding image from Sentinel Hub and just store it here in our folder. Next, let's also visualize this kind of information. And therefore, I just picked up the very first patch ID here that is stored. And over here, you can see now the time series that we have downloaded. So for instance, here in this case, we just took the very first 8 time points from our series. And you can see it's the same area, it's the same patch, but just over time. And you can also see the different artifacts, different colors, also cloud coverages that we can see over here. Now that we have set up this or downloaded the Sentinel-2 imagery, we have a data set with rasterized Sentinel-2 images. I have a certain patch size that can be used in our machine learning model. So the next step would be to train and set up a machine learning model. So in this example here in this notebook, we rely on PyTorch. That's a very common deep learning framework. And here are first some imports that are required for this library. Then in the second step, we define the model architecture. So in this notebook here, we used a convolution LSTM. This is from the previous webinar that we gave, showed to be the best for learning this temporal dimension, the temporal dependency between different Sentinel images, and also yielded to the highest accuracy for this forest map that we evaluated. So for this model, we basically use the typical module here from PyTorch. We first define a conv-LSTM cell itself. So the main part here is that it's using here a convolution, a 2D convolution inside the LSTM cell. And with this cell, we can now define here the convolution LSTM network, which is using internally as a cell operation this convolution operator over here. And in the forward step, that is the most important one here, we are basically iterating here over the time, so over the different time steps that we get. Basically, this is the multi-temporal Sentinel-2 images. We forward, get the hidden and the output state, and then finally have here the classifier for the output. So this is the model that we're using. It's a small model for this notebook so that everyone can also run it. And in the following here is it's just a very small function to get this, to basically get a utility function to just get the network instance here. Now the next step that we are using is the inference part. So we don't go into detail here on how you can train this model. So that's something that is not really related to GeoPackage or EOLearn. So once you have your data set, and this was from the previous step, you just take your rasterized ground truth data, and then you can just use the typical cross-entropy function loss and train your network. In this notebook here, we also provide you with a pre-trained network so that you can directly run it for the next step for the inference part. So therefore, again here, we first check if you have a GPU available or you want to run it on CPU. Then again, we define first a EO task. In this case here, it's an inference task, which is basically loading the network model. It's loading the weights that we give, and then just adds to the EO patches the network prediction and returns the EO patch. So for getting the weights, again, as in the previous example, we have everything here available on the AWS bucket, this VE forest model. So here you can get the complete model itself. And then the next step would be just to create this inference task. You pass your model file. In this case, you can use our pre-trained weights. Again, you define a save task for getting the predictions. And then the workflow would be very simple. You just load one patch. You apply the network on this patch so that you get from the input of the Sentinel-2 imagery to your segmentation mask, and then you just store it again. And with this workflow, we can also, using the same 16 patch IDs, we apply this workflow here for these tile IDs. And in the next step, we can then go over and visualize and see the output. So first of all, let's visualize the input data for one time step. So this is what you can see over here. So these are the, I hope you can see it, it's the 4x4 patches that we selected. Here you see the city of Kaiserslautern and around the forest areas. And in the next step, we here first define a function for converting the class predictions into a more meaningful color encoding, basically. And with this encoding, in the next step, we can now again go over our predictions for the same input data. That's what you see over here. So we load here the predictions and then just visualize the labels. In this case, it's a binary forest map, what you can see over here. So yeah, you can see it's working really good. And in the same step, so the network was also trained with additional information, for instance, also coniferous and broadleafed forests. So we can also use this information, again, go over the predictions and visualize it. And now we see here also the different types of tree species that we're generating here. And the next step would be then to have a closer look also if you want to compare the time series for particular times. You can just use the input data here, visualize it, your predictions, and get some deeper insights in it. And of course, if you have different areas or a different use case, you can also apply it on a larger scale. And this is also what you can see over here. So this is, for instance, running over complete the German area and also nearby countries. Then you would get something like this one here. And of course, the very large application is something that you can see over here, where we run it over the complete European surface. Yeah, and with this, I would like to finish up this notebook and give over to Devis.
Thank you, Benjamin. Hello, everyone. I would proceed presenting then our part on the hierarchical object detection, which you've heard about in the first webinar. Today, what we would like to show you is mostly three things. So first of all, an overview of what we open sourced. Second, we'll have a bit of a deeper look at actually the Yector codebase and what it allows you to do. And lastly, we're going to look at the Jupyter Notebook, which allows you to run end-to-end inference. So what it was open source, so we have mostly three things. So the models and the labels for Dakar, which are published in the QueryPlanet AWS S3 bucket. So you will find there all the material that was generated sort of by QueryPlanet. So you've seen in Benjamin's notebook, basically is pulling the models. So here you will find in the same location the material for Yector, which is published under a Creative Commons non-commercial license. Furthermore, we published the code for Yector, which allows you to do both training and inference on the Sentinel Hub Yector GitHub repository under MIT license. And as well, we have then the notebook, which I will show you in about 10 minutes, where you can run again the full inference. So you will find this in the year-learn examples. And you will find in the year-learn examples also Benjamin's notebook and what Ivan presented you. So this will be later on in mid-May. So these are sort of the locations that you need to look for. The QueryPlanet open bucket where you can pull the material from, and the year-learn examples where you will find the notebooks. So what's in the Yector codebase? So as mentioned, all the codebase will allow you to reproduce both the training and the inference steps. So this is sort of an overview of the content. There are a few requisites. So the first is Sentinel Hub account. You can get free trials for it. And the second part is credits, so that you can order and buy very high resolution imagery. Regarding the storage, so again, this is a tool meant to work for large scale, which means huge amounts of data. So hundreds of gigabytes, if not terabytes of data, which is sort of not feasible to store locally. So the code uses Amazon Web Services and in particular the S3 buckets to allow sort of centralized storage of the objects, and EC2 spot instances, so that actually inference can be parallelized over CPU machines and run sort of in a scalable way. So you could adapt this sort of to different cloud providers, but you would have to sort of put sort of some effort in replacing the Amazon Web Services with your cloud provider of choice. And also for training, GPU is of course recommended for a more fast convergence of the models. So Yector uses the does object detection of oriented bounding boxes and uses the single stage rotation decoupled detector, which was recently published and proposed. And what the SSRDD algorithm does, so is based on a ResNet backbone, so pre-trained weights from ResNet, and uses a feature pyramid network, which means that it estimates sort of, it does prediction of objects, so it does detection of objects at different scales throughout sort of the ResNet architecture. And then these are combined together to get the final predictions. So it's sort of inherent multi-scale approach. And SSRDD encoded the oriented bounding boxes as a combination of axis-aligned boxes plus the smallest angle that basically aligns the oriented bounding box to an axis-aligned bounding box. After sort of both the training and the prediction, so the algorithm makes a lot of sort of guesses for where the bounding boxes are. And what is then applied is this non-max suppression algorithm, which is typical sort of run in object detection. And what this does removes basically the least confident detections that overlap to a large degree to other detections. So basically, this is an example of an output before non-max suppression, and then basically it removes all the overlapping non-confidence predictions to leave just one or very few. Why do we mention this? Because when you need, basically when you will install the package, you need to compile code for this non-max suppression in order for it to run sort of in optimized and efficient way. So these otherwise are the instructions to get going, so to get started and allow you sort of to run the code. So first you need to set up your Python environment, and basically you could use any environment of your choice. So it should work with virtual environment, PyEnv, and Conda as well. After that, you clone the Sentinel Hub Yector repository, and you just install the directory with pip. And if you want to get sort of development modes, if you want to edit and improve the code, you just install it with the development flag. As mentioned, this non-max suppression needs to be compiled, either whether you are on CPU, so running inference on CPU, or running training and inference on GPU. And there are instructions on how to do this. And there are two more sort of prerequisites. If you want to do training, then you need to download the ResNet pre-trained weights. This can be easily found in this case. So the code uses Torch. So you will find quite easily ResNet's pre-trained weights for Torch. And if you do inference, as sort of we meant this tool to be used for very large scale and very parallel inference, we provide a Docker image which can be built, which then will be deployed in the Spot instances by array cluster. So then you can scale the prediction in an efficient way, sort of automatic and efficient way. And this is provided within the package. So just an overview of what then you can do. So the first phase is training your models, your object detection models for the different data sources. So in our case, what we will provide, sort of what we've built the prototype for, was using Sentinel-2 data, Airbus Spot, and Airbus Pleiades. So you will see these three data sources mentioned in the code. And so we have an area of interest. What we do, we split it. In this case, sort of this training is applicable to any data source. So we did this for Sentinel-2, and then likewise for Spot and Pleiades. So you can do this separately, or also do this together. So for instance, Spot and Pleiades, we trained a joint model for the two data sources. So then you split your large area of interest into smaller patches, which are manageable, and we can run this in a parallel way. We download the data of interest, and we add the reference, in this case, the building footprints. And we store this on a bucket, and you will find utils to do this. This is an example, for instance, for Pleiades with building footprints. And once we do this, we further split this. So these are stored as EO patches on a bucket. So we have the data, we have the reference. And what we do, we split these further into smaller image chips of different sizes, which sort of, this is the AI-ready data set that the model will use through data loaders. So we split these EO patches into smaller EO patches where you can define sort of your size and scale. And these are stored in NumPys, the images, and JSONs, the labels. And there's a script which allows you to run this sort of programmatically. And we save this result on a bucket. And once we have this, then we run 3 steps. So first, we split these into train, test, and cross-validation. So we do k-fold validation. So the code allows you to do k-fold validation, normalization, so that the model can generalize to larger scale and also to different data sources. And then we proceed to train our SSRDD model. And again, we save the model on the bucket. So then you don't need to transfer the data sort of locally, so the model can train directly from data on the bucket. Also, the model goes on the bucket so that we can basically run parallel inference and read directly from this centralized location. So we can repeat this for the data sources that we want to analyze. So in our case, we have an SRDD for Sentinel-2 and a single one for both Spot and Pleiades. So once we have these trained models, what we do for inference, then we have our AOI. First, we split it and we download Sentinel-2 imagery, where we're going to find build-up areas. So then we run inference in parallel. Again, we use array cluster to parallelize over all these EO patches to scale it and get it in a sort of efficient and timely manner. And you'll find this script array predict. So it does, starting from the EO patch, it does sort of all the process that we've seen before. So splitting into smaller image chips, normalization, so it does this on the fly. So this intermediate data is not saved. What is saved are just the output. So what we get then is our estimates of built up areas. And once we have this, then we can sort of proceed with the zoom in. So once the model trained on Sentinel-2 finds built up areas, then we look at those areas only, and we request error by spot imagery. We store the EO patches on the bucket, and again, we run on the fly this ray predict script, which then will generate object detection on spot. Then, if you remember, we run sort of an estimate of where we would need higher resolution imagery with this drill down index. And on those found areas then where we think we need basically higher resolution imagery, then we proceed ordering and downloading Airbus Pleiades using Sentinel Hub service. And again, then we can apply the train model for Pleiades to get estimates on the higher resolution imagery. So now we will move on to the Jupyter notebook that shows exactly the last part. So running inference, so say we have then the train model which we provide, and you have an area of interest and you want to run the detection. So I will show you then how you can do this. So this is the notebook that you can find in your Learn Examples, Hector folder. And as mentioned, there are a few things that you need to sort of set up, but most of these things actually are customizable to your data source of preference and, for instance, cloud service provider. So we have a section where we have constants and utility functions. So here you will define the sort of parameters both for splitting your area of interest for Sentinel-2, Spot, and Pleiades, your time interval, and of course the directories, name of the directories, and few other things, such as the drill down index, which again is customizable, the pixel size of your data sources. So and for instance, the credentials for your AWS S3 bucket. Here you can run this notebook locally, actually on your laptop. So this notebook was actually run on a laptop, so you don't need sort of very large resources. Of course, we will do it just for a small, very small area in Dakar. Of course, if you want to run this on a large scale, you need sort of more resources. But this was designed again to run sort of on CPUs, but sort of many of them and many instances, even though basically running on CPU. So in this case, then you can leave this if you're running this locally. So the file system is the local file system. Otherwise, you can use the file system on AWS S3. So if you use another cloud provider, you would have, for instance, to implement this interface to your cloud provider. Then we have credentials for Sentinel Hub, and then we are ready to go. So these are some utility functions, And the first thing that we're going to do then is split the area of interest. So this is an outline of the car. And we start splitting this into smaller chunks. And we're going to download Sentinel-2 imagery for each of these EO patches. And we do this again. We have utility functions that allow you to do this quite easily. And in this case, there were 15 EO patches, but we're going to run it only for one. And this is the result. So this is the Sentinel-2 imagery. And now we're going to run inference on this. So we pull the material, sort of the weights from the bucket. So you see this is the QueryPlanet open public bucket. This is the config file that is required to run inference. So this is all you need basically to run inference, and you have to make sort of very little modifications to run it on Sentinel-2 spot sort of for the data sources. So here you will specify basically where you have the EO patches and some parameters used to define your architecture. Once we have this config file, we can run the prediction using Ray sort of on the fly. In this case, it will use only sort of one cluster, your local machine. And the algorithm, sort of the model, then produces estimates of so object detection estimates in a given file, which is this data file, which is basically text files for a benchmark data set, which is called data. So what we do, we convert these to vector polygons. So we convert to geo packages and we merge them to have sort of a single raster image. And we also sort of then vectorize this so that we get a vector polygon that identifies built-up area, which you see here in yellow. So if we run this on the whole area of interest, we'll find areas of built-up, and we can focus on these areas then to order and download imagery at higher resolution. And we do this with Airbus Spot. So you see then we further split into a finer grid the area that we defined with Sentinel-2, and these are the EO patches. Now we will focus only at these 2 EO patches. So we order and download spot imagery through Sentinel Hub service. So the third-party data import, and then we can treat whatever data source as any data collection, and we can use the Sentinel Hub API to retrieve the data. So we do this for spot. So you see now we got spot imagery, and likewise we pull the pre-trained model for spot. We set up the inference config. So again, with these configs and the scripts, you can run this from command line and you can automate the process, and we can get then the object detection estimates for spot. So you see in some areas for larger buildings, they're sort of more accurate, of course, than for very packed areas with some false positives. So just a reminder that these models were fine-tuned on a very small number of buildings, around 6,000. So there is large margin for improving the performance. Once we have the spot predictions, then we compute statistics on them, and we further split the grid so that we can find areas of very sort of packed, low confidence estimates. And these are the areas where we're going to order and request higher resolution imagery. So our Airbus Pleiades imagery, and we're going to do this for these EO patches marked sort of in yellow, so in darker red. And so we repeat the process. Then we order, we download the imagery. In this case, we had imagery available for the entire AOI, so we request those. Otherwise, you would get imagery just for the smaller EO patch. The rest would be no data. And once you have this, again, config for Pleiades, and we get predictions for Pleiades imagery. In this case, we use the same model, so the same model can predict both on spot and Pleiades. And once we have these, we can merge then the predictions, and we're going to take the spot predictions for where we determine they're good enough, and for where we have Pleiades imagery, we will use the Pleiades estimates. And this is the final result, that then for your entire AOI, you will combine spot predictions and Pleiades predictions. And with this, I would like to thank you for your attention, and I would give the word back to Sabina.
Thank you, Devis, and thanks to all presenters. Thanks goes also to all of you attending and asking so many good questions in the chat. As mentioned at the beginning, we are not answering questions live today, but we rather invite you to write to our presenters directly, or even better, use our Sentinel Hub forum, or comment the recording which will be published later on YouTube. For more information, you can also check out the displayed links on EOLearn and Sentinel Hub accounts. In case you don't already have an account, a Sentinel Hub account, you can create a 30-day trial. And if you need more processing units than the trial provides, just contact us and we will extend the limited units. In case you're conducting research, or if you are in a pre-commercial exploitation phase, you can also use the opportunity to apply for ESA-sponsored accounts and access to high-resolution commercial data. And this is available through the Network of Resources program, and you can see all the links which are provided for details. That would be all for today. Thank you for attending, and have a nice day.